Hey guys, so welcome back to your next class of Catalyst Concepts. Today we are going to continue with where we left off last time. So we're taking a look at the periodic table of elements, the modern periodic table to be more specific, and we looked at what the group and periods would signify for us, right, horizontally and vertically, what we can see. So we're going to start discussing about what trends or what patterns that we can see when we look at the periodic table either horizontally or vertically. Okay, so I have this periodic table over here open in this tab. So we'll be discussing two major things for today. One of them is the metallic or non-metallic properties. Okay, now so in this table you'll see that each column or each block is colored a little differently, and that is for a reason. It's all based on what kind of behavior these elements exhibit. Okay, now I want you to pay attention to these first two groups, and that is basically the S block, right? For us, the elements of hydrogen, lithium, beryllium, sodium, magnesium, potassium, calcium, rubidium, strontium, cesium, barium, all of these are S block. And then if you move to the other end of the table, you have these boron, carbon, nitrogen, oxygen, fluorine, chlorine, sulfur, selenium, bromine, all of these elements over here. Right now, since these are two opposite ends of the table, there is a very clear contrast in how they behave. Okay, so these starting few elements are actually metallic in nature, right? For example, magnesium, for us we know magnesium is a metal that we use. Similarly, sodium is also a metal, although we've never actually used it or seen it in metallic form, but it does behave like a metal. If you look at the other end, you'll see chlorine, fluorine, bromine, iodine. All of these are what we call as non-metals. Okay, so one very clear observation that we can make is that as we are looking at the horizontal periods, that is basically from left to right of the table, at the beginning our elements are metallic in nature, and by the ending they are non-metallic in nature. Now what exactly makes them metallic and non-metallic? Let's try to understand that. That will help us understand this property better. So if I take a metal like lithium, right, I just simply draw the Bohr model for it. So lithium for us looks something like this, right? 3 electrons. So if I take lithium, okay, something wrong. Okay, right. So when I use lithium as an example, what I'm trying to do is I'm trying to show you what exactly the atomic structure look like from here all the way till the ending. Okay, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So fluorine is the element that is at the other end of the same period. That will be the second period. Now fluorine looks something like this: 5, 6, 7. So 9 electrons, and that is fluorine. Now, when an element has about 1 to 3 electrons in the outermost shell, then we say it will be metallic in nature. Okay, if it has only 1 to 3 electrons in the outermost shell, it is metallic in nature. If it has 4 or 5 or above, we say it is non-metallic in nature. Okay. Now, why this is metallic and why this is non-metallic is whenever elements have 1 to 3 electrons only, it's easy for them to lose these electrons or to give away these electrons. And that is a property that we call as a metallic property. Okay, metals find it easy to give out electrons. So that is why the initial elements on the left side are metallic in nature. And as you go forward, we know that you keep adding electrons while you go to the right, correct? So initially from 1 we start to 2 electrons, 3, 4, 5, 6, 7, 8, all the way till the end. It means that as the electrons are increasing, the metallic property is reducing and they become non-metallic in nature. So what I can say is, when I go from left to right, I can say metallic nature decreases. Okay, meaning these are very strong metals. Then the one after that are a little bit less strong metals. The one after a little more, and all the way till the ending, where they are not at all metallic. Okay, we can also call this as non-metallic nature increases. Okay, because if metallic decrease, non-metallic has to increase. They're kind of like opposites. Okay, this is about across the period. What about down a group? Okay, from top to bottom. So if I talk about this, I'll have lithium, I'll have sodium, I'll have potassium, I'll have rubidium, I'll have cesium. Okay, so I'm looking at the first column over here, including hydrogen also, but that's a little debatable. So of these elements, which are they are all metallic for sure. All of them have only one electron outside. But which one is more of a metal, which one is less of a metal? Okay, I can say that cesium is more metallic than lithium. Okay, so as we go down, we say that metallic nature increases. Okay, as we go down, metallic nature will increase, or we can say non-metallic will decrease. Either way, it means the same thing. The bigger the atom, the more easy it is for it to lose electron. That is why we say that these are more, cesium is a big atom, so it's easy for it to lose an electron. So it is more metallic than lithium, which is a very small atom, and it's a little difficult for it to give away its electrons. Okay. So this is about metallic and non-metallic properties in a periodic table. Now, if you look at the periodic table, you'll also have certain names that go along with these groups. Okay. So if you see, the first column has this light orangish color. They're called alkali metals. The second one is a little darker orange called alkaline earth metals. Okay. So alkali metals and alkaline earth metals. It's in the name. This purple table over here in the middle, these 10 are called transition metals. Okay, we call it transition because that is where you see the shift from metallic to non-metallic. So the kind of the transition metals. As you go to the end, these green ones are called halogens. Okay, it's again a type of a non-metallic group, halogen group. Each group will have a certain type of a name. Noble gases are something we'll discuss later. There's like basically just look at all of these names that come for everything. Over here you have something called non-metals and metals. Okay, so basically these pinkish area are something called metalloids. Okay, they kind of show a little bit of metallic nature, also a little bit of non-metallic nature. That's because they're in between exactly what the border of metals and non-metals, right? So we call them as metalloids. Okay, the yellow colored bar that you see over here, like steps, that is where the division happens. So the more close an element is to it, the more dual property it will show of both being a metal and a non-metal. Okay, so metals then slowly becoming metalloids and slowly becoming complete non-metals. It's a whole segment. All right, let's move ahead to the next property that we'll talk about, and that is valency. Okay, now what is this valency? This is something that we have studied before, right? We know that valency is the combining power of an atom or of an element, right? It simply tells us how many electrons or how many other atoms it can combine with. Or if we talk about electrons, we can say how many electrons can be exchanged by this whole atom of the element. For example, we know that sodium has a valency of +1, right? We also know chlorine has a valency of -1. Okay, so when we talk about valency in the periodic table, in the first column we have one valency. Okay, it's a positive valency, but the value of it is 1. Okay, now as we go towards the right, the valency keeps increasing. Okay, 1 to 2, then to 3, all the way up till 4. Okay, once it hits 4, it starts to reduce again, 3, 2, 1, and in the ending it becomes 0. Okay, so if I look at the elements over here, lithium is 1, beryllium is 2, boron is 3, carbon will be 4. Then after that, nitrogen becomes 3, oxygen is 2, fluorine is 1, and neon is 0. Okay, this entire ending column has 0 valency, basically because they do not react with anyone. They have no combining power. Now, this is the trend in valency when you see across a period. It will increase all the way up till 4, and then it will reduce from 4, 3 to 1. The first half are all positive valencies, the second half are all negative valencies. Okay, now we generally don't consider that for this D block, this transition block, because they have something called variable valencies. Their valencies can change depending on what type of combination reaction they are doing. Okay, so this generally trend applies only for S block and P block. We don't count the transition block or the D block or even the F block inside this. Okay, all right, so that's it for today. We learned about two properties. Okay, before I forget, what about down a group? Good question. Is we saw across a period valency increase, then decrease, right? What about down a group? What about lithium, for example? The same thing: lithium, sodium, potassium, rubidium, cesium. Will the valency increase, decrease, or not? Valency does not change when we go down. If I see lithium also has 1, sodium also has 1, potassium, rubidium, cesium, all of them have the same valency. So when we look down in a group, valency does not change. Okay, because they're all in the same this thing, right? Same combining power. All right, okay, so that's it for today. I'll stop here. Tomorrow we'll look at a couple of more properties, and if you have any questions, doubts, please drop them in the comments below, and I'm going to see you again in the next class. Thank you so much.